All right, let's dive in. Today, we are going to pull back the curtain on a core piece of the Linux file system that's super important, but, often a little misunderstood, the inode. If you've ever really wondered how Linux actually handles files under the hood, well, you're in for a treat.
So we're going to kick things off with a classic, and let's be real, a super frustrating Linux mystery. You're running out of disk space, you find a massive log file. I'm talking a multi-gigabyte beast. You delete it, you run dfhr, and nothing. The space is still gone. So where did it go?
The key to solving that mystery and to really getting how Linux manages files is this little data structure called an inode. Think of it as the invisible engine running behind every single file and directory on your system.
So here's our game plan. We'll start by solving that disappearing space problem and figuring out what an inode even is. Then, we'll get into the whole name versus ID thing, which flows right into hard and soft links. After that, we'll see how this all plays out in the real world and wrap up with a few essential commands for your toolkit. Okay, first things first. What exactly is this thing we're calling an inode? It's not just some abstract concept. It's a real, fundamental building block of file systems like X4 and XFS. At its heart, an inode is just an entry in a big table, kind of like a single row in a giant spreadsheet that the file system keeps. Every file gets one row, one entry, one inode. And this entry doesn't hold the file's content. Instead, it holds all the metadata, the data about the data.
So the inode knows pretty much everything about the file. It keeps track of the permissions, who can read, write, or execute it. It's got the owner, the size, all those important timestamps. It also keeps a little counter for something called hard links. We'll talk more about that in a bit. And most importantly, it holds the pointers, the literal map to where the file's data is physically sitting on the disk. But here's the kicker. Look at what's not on that list. The file name. This is probably the single most important and, honestly, the most surprising thing to get. The inode, the very identity of the file, has no idea what you decided to call it.
So, if the inode doesn't store the file name, where is it? And how does the system possibly connect the name you type, like myscript.sh, to the actual file? Well, this brings us to the really important difference between a file's name and its real identity. So how does it all connect? Well, a directory isn't some kind of magical folder. It's really just a special file itself, and its only job is to hold a list that maps the human-friendly file names to their corresponding inode numbers. So when you access a file, the system just looks in the directory, finds the name, grabs the inode number, and uses that number to find the actual inode and all its data. Here's a great way to think about it. The inode is the file's permanent ID card. It's got a unique number, and it's what the system actually uses to find it. The file name? That's just a nickname. It's a convenient, easy-to-remember label that points to that ID card. And just like a person can have multiple nicknames, a single file can have multiple file names. And this whole idea of separating the name from the ID, well, that's what makes one of the most powerful features in Linux possible, links. And once you get the inode, you finally understand the difference between hard links and soft links. Okay, so a hard link is literally just another nickname for the exact same ID card. You have two completely different file names, and they both point directly to the very same inode number. They're total equals. There's no original and link. If you delete one of the file names, the other one still points to the inode, and all the file's data is perfectly safe. The file only gets deleted for real when its hard link count, which, remember, is stored in the inode, finally drops to 0. A soft link, or a symbolic link, is a whole different animal. It's not another nickname. It is a brand new, separate file, and it has its own unique inode. And the data stored in this new file? It's just the text of the path to another file. It's basically a shortcut, just like you'd see in Windows. It's not pointing to the inode. It's pointing to a file name.
All right, let's put them head to head. Hard links, they share one inode. Soft links, they each have their own. Because hard links are tied to the inode table of a specific disk, they can't cross from one file system to another. But soft links, since they're just storing a text path, can point anywhere they want, even to a file on a network share. And here's the big difference. If you delete the file a soft link is pointing to, the link breaks. It becomes a stale or dead link that points to nothing.
Okay, theory is great, but why does any of this matter in your day-to-day job? Let's bring this back to some real-world headaches you've probably run into.
Which, of course, brings us right back to where we started. You run RM on that huge file, but your disk space doesn't come back. What is going on?
The secret is that some running process still has that file open. You see, when a process opens a file, it gets a file descriptor, which is like a direct, private link to the inode. When you type RM, all you're doing is removing the file name, the nickname, from the directory. You've removed one link to the inode, but that process's file descriptor is another link. The kernel won't free up the inode in its data blocks until every single link to it is gone. That space only gets reclaimed once the process holding the file open finally closes it or gets restarted.
Now for a second, much sneakier problem, inode exhaustion. This is what can happen when you have millions and millions of tiny files, like for caching or user sessions.
And this is the painful result. When you format a drive, it sets aside a fixed number of inodes. If you create millions of tiny files and use up every single one of them, you'll try to create a new file and get an error like no space left on device. Even when df-h shows you've got tons of free space. You've literally run out of ID cards for the system, so it can't register any new files.
So how do you actually keep an eye on all this? Let's get you set up with a couple of essential command line tools for your inode toolkit. The first tool is super simple, ls-i. That little -i flag just tells the ls command to print the inode number right there in the first column. This is the perfect way to see which files are hard linked to each other. Just look for any files that share the same exact inode number.
And this command, this one is an absolute lifesaver for that inode exhaustion problem. You already know df-h shows you disk space, right? Well, df-i shows you inode usage. It'll tell you the total inodes, how many are used, how many are free, and most importantly, the percentage used. If you see that number creeping up towards 100%, you know you've got a problem brewing.
So let's just quickly recap. The most important thing here is that the inode is the file's true identity, its ID card, while the file name is just a convenient label. That's why hard links can be perfect peers, while soft links are just shortcuts. And finally, please don't forget that you have a limited number of these inodes, and running out can bring your system to a grinding halt, no matter how much disk space you have left. And that's a wrap. So I'll just leave you with this one thought. Now that you really understand this deep connection between file names, inodes, and data, how might this change the way you design a system for managing application logs or creating really efficient backups? Something to think about. Thanks so much for watching.